Welcome to Cyclopod, showcasing work by early career geoscientists that is of interest to the cyclostratigraphic community. This podcast is made possible thanks to financial support of the International Subcommission on Timescale Calibration. Hi there, welcome to the 11th episode of Cyclopod. This week, our guest is Anta-Clarisse Sarr from Sarr in Aix-en-Provence in France. Anta-Clarisse, correct me if I'm wrong, but I don't think you identify yourself as a cyclostratigrapher, right?
No, not really.
In an earlier life, Anta-Clarisse did some work on seismic stratigraphy, but in my eyes, Anta-Clarisse, she is primarily a paleoclimatologist and a paleoclimate modeler. And the paper that we are going to talk about today is indeed a modeling paper. This paper was published in April this year in Nature Geoscience, and therein, Anta-Clarisse reports on a series of early and late Miocene sensitivity experiments with the French Earth System Model IPSL. She tested a number of topographic boundary conditions in East Africa, the Middle East, the Himalayas, and the Tibetan Plateau. And with her results, she could reconcile several different hypotheses on the evolution of the South Asian monsoon. So to be clear, none of these sensitivity experiments, they looked at the climate effects of Milankovitch cycles or astronomical forcing. Anta-Clarisse focused on topographic forcing. So why on earth did I invite Anta-Clarisse then? Well, her modeling paper was very well received by several cyclostratigraphers, including me. And the paper has major implications for Miocene cyclostratigraphy and paleoclimate on astronomical timescales. So, Anta-Clarisse, a very warm welcome to Cyclopod. How are you doing?
I'm doing fine, thank you. I would, however, like to correct something. I'm not seeing myself as a full paleoclimatologist, but let's say for this Cyclopod at least that I can be paleoclimatologist sometimes.
Yeah, everyone has several hats to put on, and I think a very nice hat or a hat that really looks good on you is your paleoclimate hat.
Perfect.
So the idea of today's Cyclopod is that we will go through all of the previous episodes that had a Miocene link. In total, that were 3 episodes. Last year, we had Zichang Wang with his lacustrine and Aeolian section in Tibet. Then we had Anna Joy Drury with her 30 million year long time-continuous Walvis Ridge study. And earlier this year, we had Boris Karatsolis and Clara Bolton talking about the biogenic bloom. And so we'll be looking at your modeling results, Anta-Clarisse, from the perspective of those 3 Miocene papers. Is that okay?
Yeah, that's fine.
But before we do that, I want to make the link with one of my recent papers. In 2020, I published a study on the leads and lags between benthic oxygen and carbon isotopes. In that paper, I showed that under normal circumstances, climate is leading the carbon cycle. So that means that climate changes on astronomical timescales are causing changes in the fluxes of carbon between different carbon reservoirs. But from time to time, climate appeared to be lagging the carbon cycle instead of leading it. Those times of carbon cycle lead, they occurred during eccentricity minima prior to 26 million years ago, so prior to the early Miocene. But those carbon cycle leads occurred during long-term eccentricity maxima after 26 million years ago. So in my paper, I ascribe those shifts in the response to the grand cycle in eccentricity to a shift in the weathering locus from the high latitudes to the low latitudes. Of course, this is connected to the intensification of the Asian monsoons in the latest Oligocene and early Miocene. So that made me wonder, does your model have a climate-dependent weathering component, and how does it behave in your simulations?
Well, unfortunately for you, I am using an Earth system model that do not have any continental biogeochemistry module, so no weathering. But this model only simulates ocean and atmosphere dynamics, vegetation dynamics, as well as ocean biogeochemistry only, as for all the other models of similar type. So even in the ocean biogeochemistry model I use in my monsoon paper, the nutrient input that comes from continental weathering is only scaled off to a runoff. So it's like when climate is changing, we likely partly account for the change in the location of precipitations area that would eventually generate modification in weathering. But this is the only thing we can do so far. More work is clearly required to include realistic weathering module, like I know that, and also to generate more realistic weathering fluxes toward the ocean. And we are like trying now to run geoclim simulations. So geoclim is a specialized continental weathering module. And we hope that with that kind of framework, we will be able to derive weathering fluxes that we can then put in the ocean model and see what happened in the ocean. But we are not working on oligomycin, unfortunately for you.
Yeah, but I'm looking forward to see weathering components fully integrated in Earth system models. Now let's go back to our earlier cyclopod episodes dealing with the Miocene. So first of all, we'll be talking about the work by Zichang Wang. And Zichang Wang, he wrote the following about the late Miocene on the Tibetan Plateau. He wrote, 100 kiloyear eccentricity cycles in the lacustrine section were mainly controlled by East Asian summer monsoon variability. They may have been linked to Antarctic ice sheets or low latitude insolation modulations dominated by eccentricity modulated precessions. When I compared that finding to your simulations, then I noticed that your simulations show that changing ice volume on Antarctica or changing the CO2 level in the atmosphere does not really influence the amount of wet season precipitation in the late Miocene. Your two cold simulations, so the simulation with less CO2 and the simulation with a more extensive Antarctic ice sheet, these simulations have more or less equal amounts of wet season precipitation compared to the warm simulation. Does that mean that the result of Zichang Wang should be interpreted as a local response to local insolation patterns rather than that they are linked with Antarctic ice sheet volume changes?
Well, before answering the question, just let me highlight that Xingzhen records come from the East Asian monsoon region, where I'll mostly discuss the South Asian monsoon region in my paper. And there are two different systems, and it looks that they behave differently in response to the forcings. And apparently, East Asian monsoon domain is more sensitive to the size of Antarctic ice sheets and also to CO2 than the SAM domain is. Also, to be honest, that changes I use, especially for the Antarctic ice sheet size, in my simulation were rather brutal tests to see whether we could simulate a huge change in the monsoon system as being recorded on tectonic timescale. But like as usual, it looks like the South Asian monsoon system is rather insensitive to Antarctic ice sheets extent and is much more constrained by topographic configuration as I've shown. I did not look at huge change in the extension of ice sheet as sometimes suggested, and especially I do not investigating potential change in sea ice patterns on the monsoon system. So that's obviously something to be explored. So now to come back to the question, from my experience, however, with orbital simulation, so I did run orbital scale simulation. This is like the Luc Beaufort paper on coccolith evolution. I would say that there is some way a strong insolation component on the orbital cyclicity you see in Asia. It also have been shown by colleagues from other modeling group, like the Alan Haywood group, for example, on Pliocene and Pleistocene simulation. So I said that because we are able to simulate strong variability in precipitation in Asia related to precession at least, without ever changing the Antarctic ice sheet extent. So for sure, the insolation component is like somewhere.
Yeah, not to be underestimated in that monsoonal system.
Yeah, it's also have been shown like at all time scale. I have colleagues that run simulation on Eocene and Oligocene configuration, trying to understand the orbital signal in East Asian monsoon domain. This is the Delphine Tardif paper in 2020 in Science Advance. So you can look at that.
All right. So let's move on then. In the podcast with Anna Joy Drury, we talked about an ODP site at Walvis Ridge in the Atlantic Ocean. So not in the Indian Ocean, but I remember that there in the Atlantic Ocean, the South Atlantic Ocean, the calcium carbonate content switched its behavior on astronomical timescales sometime in the late Miocene, I believe around 8 million years ago or so. So prior to that time, in the Oligocene and the early part of the Miocene, we had more calcium carbonate in colder periods. But since the late Miocene, since 8 million years ago, we have more calcium carbonate during warmer periods. So that's the switch there. And of course, there is little doubt that a change in ocean circulation played an important role in causing this switch in calcium carbonate response to astronomical forcing. Can you somehow connect your results, your modeling results regarding the Somali jet and the upwelling and the westerly shear over the Indian Ocean with what Anna Joy observed on Walvis Ridge in the South Atlantic Ocean?
This is a highly difficult question because Walvis Ridge is so far away from tropical Indian Ocean. So I would say that there is little chance that what I've been looking at on Arabian Sea dynamics has any impact on what Anna Joy is seeing in the Atlantic Ocean. But the 8 million year date seems to be also highlighted in the Arabian Sea region, if I remember well, although it might not be up to date because lots of work have been done, especially by the cyclo community in the last years. So I guess that this date also appear in other records probably. And if it's the case, it would suggest that strong changes in the global pattern of circulation are to be the cause, although they can also superimpose with local changes. So for the Arabian Sea, I would say that probably the 8 million date is also associated with intensification of monsoon circulation that can be related either to ice sheets dynamics, CO2 decrease, or a change in topography in the Iran-Zagros region that might have become high enough to fully block the dry winds from the northeast, from Eurasia entering the monsoon domain, as I've shown in my paper, but as also suggested by Acosta and Huber 2020 paper. So maybe those changes have been kind of responsible to cross a threshold in the system, but I'm not sure how much those localized changes within the Asian monsoon system might have been contributing to the global ocean circulation. Other events also likely happened during the Miocene, and to my opinion, they are often kind of left aside, and especially seaways have been evolving, although we often forgot about that, like Central American seaways is not well constrained on that time period. Greenland, Scotland Ridge also have played a role, although like we still have more to discover on that peculiar seaway, and other seaways probably also have a role. So I think all those seaways have much more potential to generate strong change in the global circulation than mountain belts I've been studying. Ice sheet dynamics can also have played a role some way, as Anna Joy suggests, I think, in her podcast. So I would say that the first thing we should probably look at is all those mechanisms. We can maybe try to figure out what we can say from modeling simulation.
Maybe a side question on this note. In your Earth system model that you've been using, how well is ocean circulation resolved? Because I guess that you work with a relatively coarse grid, right?
I mean, the grid size is 2 degree by 2 degree, except in the equatorial region where we can go up to 0.5 degree, which is pretty nice. So I would say that globally, like the general pattern are very well resolved. Although it has been shown lately that using much more higher resolution model can give us surprising results.
Yeah. But you have the big picture correct in your Earth system model.
Yeah. To end up on this peculiar topic, I would say that we have to be careful trying to attribute changes in ocean biogeochemistry at one peculiar site to one geological event, because like one geological event like seaways changes can trigger a whole set of both global and local phenomena that then would impact one single site.
then let's dig a little bit deeper in that biosphere component that you just touched upon. In the podcast with Boris Karatsolis and Clara Bolton, the late Miocene-Pliocene biogenic bloom comes into focus. And Boris Karatsolis compiled a global data set of primary productivity, and he reports very high calcium carbonate mass accumulation rates in the late Miocene. It seems like at that time, all ingredients were available to sustain high productivity on a global scale. And the Miocene was, of course, wet and warm in the low latitudes. And on top of that, we had the topographic effects in East Africa and the Middle East that caused upwelling in the Arabian Sea. How do you look at the problem of the biogenic bloom, and how was it possible to sustain such high productivity for such a long time in the late Miocene and the Pliocene?
So fun thing is that I wasn't familiar with the biogenic bloom up to last year, but we have a PhD student working on that. So to better understand why this event lasts so long, we need to investigate both like how it starts and how it ends. And those causes might be different, obviously. Not being a specialist of that kind of stuff, I still have the feeling that this is a difficult problem to tackle. Recent paper that try to explore potential change in global oceanic circulation and its effect on the bloom, like switching from Atlantic-dominated circulation to Pacific-dominated circulation, is something really interesting that we definitely should look at together with other factors such as change in nutrient input. How do I look at the problem of the biogenic bloom? Again, from modeler point of view, is rather difficult because we can set up simulations saying okay, we will try to understand how these peculiar mechanisms can help sustaining high productivity in the ocean. But the main issue is that we need to generate boundary conditions for our model so we get closer to the late Miocene condition. And it can be tricky when it comes to knowing the depth of the seaways or knowing where dusts are coming and from where they are coming. And so there are plenty of hypotheses we can try. And I think we as modelers should really take the opportunity to run new simulation based on all the hypotheses cyclo stratigrapher have drawn.
Yeah, we're good at that, right?
Yeah, and see what's going on. I mean, we can try several stuff and then see, okay, this peculiar configuration can generate high productivity, this one cannot. Yeah. And then try to figure out what happens, as I did in my monsoon paper.
Yeah, excellent stuff, Anta-Clarisse. Thank you very much for this very nice chat. I was really struck by the fact that Anta-Clarisse's modeling results, they have so many implications for so many data papers on Miocene paleoclimatology. I am pretty sure that her Nature Geoscience paper will become a landmark paper for the Miocene community. So please, Anta-Clarisse, continue doing such important modeling work, linking the evolution of the geosphere with that of the climate system and the biosphere. I am already now looking forward to reading your next paper. So thank you very much again for the interview. And at this point, I would also like to thank our audience for listening to this 11th episode of Cyclopod. See you next time.